0, the car starts decelerating, and the distance covered towards stopping is 0. So that's why in our case, C sub 2 is 0. Because when time is 0 and the car starts decelerating, the car has not covered any distance towards stopping. So that's the reason why when t is 0, S of t is 0. And that gives us C2 equals 0. So now we can determine the distance, S of 2.27. So negative 11 times 2.27 squared, and plus, well, maybe I should do the previous answer to get the best answer possible. Times the previous answer squared, and plus 50 times the previous answer, and that is the distance, 56.82. 56.82 feet. Interesting problem. Thank you for picking that. So let's go back and make sure that you understand what we just went through. So the car is decelerating at a constant rate, which means 22 feet per second squared. The velocity function will be negative 2t plus c1. We are told that at time t equals 0, when the distance covered towards stopping is 0, the velocity is 50. Awesome. So when t is 0, v of t is 50. 50 will equal c1. We plugged it in. Now they want us to determine the distance that the car needs to fully stop. But I need to find the time. So we found the time because the car stops when velocity is 0. So that's why we set the velocity equal to 0. And the time was 2.27 seconds. We determined the distance function as negative 11t squared plus 50t plus c2. And we realized that c2 must be 0. How come? Because when time is 0, S of t is 0. When the moment the car starts decelerating, the car has not covered any distance at that moment. So that's why the distance covered towards stopping is 0. So that's why C2 is 0. So in this distance function, we plugged in the time needed to completely stop, to come to a complete stop, 2.27, and we calculated, and we got 56.82 feet. Good. Perfect questions. Anything else? Okay. In that case, let's start the last chapter. That's chapter 5. So chapter 5 has a big title, but we need time to get to it. I'm going to copy it here, but I don't want to discuss anything, the name yet, just yet. It's irrelevant right now. It's called Integrals. That's the title of chapter 5. We need time to get to that. Okay. So the first thing I would like to do is go back to a few things that we discussed. Okay. If you remember, some of the graphs that we looked at in earlier chapters were asking us to find the distance covered. That's a good continuation by a particle, let's say. And so let's suppose I am given the velocity function. And we had an example. This is the velocity function. So this is f of x, velocity. So this is x, and this is f of x. So this measured in time, I don't know, seconds. and this is feet per second. So we have this function representing the velocity. If we are asked to determine the distance covered by this particle, let's say between 0 and 10 seconds, all we need to do is find the area under the graph of the velocity between 0 and 10. This area is the distance covered by the particle or car or whatever from 0 seconds till 10 seconds. So we're going to focus a little bit on area under the graph of a function. Why? Because it gives us something that we are interested in this case, distance. If this is the marginal cost, this area will be the total cost. If this is the marginal profit, this total area will be the total profit. So this is, if you want, the total distance covered. Okay. But the question is now, how do I find these areas? So this is our question for the next hour. Find area or areas on the graphs. You can say, okay, but what if I want to find this area? Can I find this area and this area? Yes. It doesn't really have to be under. It can be above or whatever, right? But for now, we're going to discuss this situation. But we can find areas. This little piece will going to be positive. This big piece is going to be negative. So the area can be negative under a graph or between the x-axis and the graph. So the total can be negative. But that's a different discussion. Right now, I want to focus on finding areas for positive functions. This is not a positive function. It's positive, but then negative. So finding areas under positive functions between this and this. And build, it's a big concept. So please try to pay attention and stop me for any questions. This is a big concept now. Okay. Again, I'm going to choose a very simple function, like let's say x squared plus 1. I am going to graph this function. Very easy. When x is 0, y is 1, on the interval 0, 2. 1, 2. 2 squared is 4, plus 1 is 5. 1, 2, 3, 4, 5. So here's the graph. The graph of x squared plus 1 between 0 and 2 is this graph. Only between 0 and 2. That's all we care about. And I want to determine this area. And for now, I'm going to say, using n, lowercase n, 2 subintervals. Okay, so I'm dividing the interval between 0 and 2 into 2 subintervals. Okay. 1 and 2. I have 3 options. We're going to discuss all 3 options. Using leftmost point, using rightmost point, and then using the midpoint. What's all this? Very simple. You're going to see in a moment. I'm going to copy it again because I don't want to go back there. Okay. So the area with 2 subintervals and leftmost point means divide the interval into 2 equal pieces in this case, unit, 1 unit, 1 unit, and use the height to determine the area of a rectangle using the leftmost point. Okay, what does this mean? So get to the function, go horizontally. Get to the function, go horizontally. I will determine the area of the first rectangle, and then I will determine the area of the second rectangle.
I'm curious, why doesn't f of x start at the origin?
Because it's x squared plus 1.
Oh, x squared plus 1. Sorry, I missed the plus 1.
Sorry, no worries, no worries. So the area with 2, of course, it's an approximation of the exact. But area with 2 subintervals on the leftmost point will have 2 rectangles. Base is 1, height. So base is 1, f of 0, plus base is 1, f of 1. We'll calculate that in a moment. I want you to see all 3 options up front. Now, with the rightmost point, I will have base times height go to the right. Base times height go to the right. So now the 2 rectangles are these. So the area with 2 and the rightmost point will still be base times height, but f of 1 plus base times height, 1 times f of 2, because this is 0, 1, and 2. We'll calculate that in a moment. The last option is this, 0, 1, 2, but the midpoint is 0.5. The midpoint is 1.5. So here's how we do it with the midpoint. Go up, hit the function, go horizontally. Go up, hit the function, go horizontally. So this is the first rectangle, and this is the second rectangle. So the area with 2 subintervals and the midpoint is still base, which is 1 times height, f of 0.5, plus still base times the height, f of 1.5. Before we calculate all this, by simply looking at the graphs, is this an underestimate or an overestimate of the exact area?
Under.
Of course, it's missing a lot of area. Good. Is this an underestimate or an overestimate of the area?
An overestimate.
It's an over. Overestimate, under. And this is the closest. Good, so now let's calculate. Remember, let's write the function one more time. So f of x equals x squared plus 1. F of 0 is 1, so 1 times 1 is 1. F of 1 is 3 plus 3, so this is 4. This is an underestimate. Okay, this one. 1, f of 1 is 2. F of 1. So f of 1 is 2. 2 times 1 is 2, plus f of 2, 5, plus 5 equals 7. Last one. 1, f of 5 is 0.25 plus 1, and 2.25 plus 1. So 425, 450. Check my numbers. I'm going to check them again. This is 0.25 plus 1. That's correct. That's 2.25 plus 1 is correct. I think it's 450. As you notice, so the underestimate, the overestimate, and in the middle. Of course, none of them is exact. They're all approximations. Now, here's a question for you. Let me see the time here. Okay, 14, that's still fine. Good. So,
Professor, I have a
yes,
question.
yes.
When you're doing the last calculation for the midpoint, where are the plus ones coming from? Oh, you're right. I'm sorry.
No, that's okay. Let me redo this. If you have any doubts, maybe you see something I don't. So 0.5 squared is 0.25 and plus 1. And 1.5 is 2.25 plus 1. So I have 4.25 plus 0.25, and I think I'm okay. Am I okay?
Yeah, I just forgot what the actual function was.
Yeah, so this is f of 0.5 and this is f of 1.5. Okay, so here's my next question. What if now I say n equals 4 subintervals? So 0, 0.5, 1, 1.5, 2. What if then I say 8 subintervals? What if I say n16? What if I say n32? Question. Do you think the approximation of the exact area with 4 is better than with 2?
Yes.
Of course. What about 8? What about 16? What about 32? Which one would be the best?
I feel like the higher the better.
Absolutely. Absolutely. So my question now is, if we talk about n equals 4, and then n equals 8, and then n equals 16, 3 dots, n equals 4,000. And what if, where am I going?
Infinity.
Yes. When we say n approaches infinity, what do we have in mind? What concept or operator we have in mind?
Limit.
Yes. So the limit as n approaches infinity from the sum of areas of rectangles. This will be the exact, equals exact area. Now we have to stop and talk about something called summation notation. We can continue before we talk about this. So in order to determine the exact area, we know how to approximate. With 4, with 6, with 8, 16, it will just take much longer, but we will always be able to approximate it. Using the leftmost point or using the rightmost point or the midpoint. It doesn't matter. The way we did it for 2 subintervals, we will be able to do it for any. But we don't want that, because still all of them will be approximations. We really are after the exact area. So if I want to determine the entire profit, and I have the rate of change of profit, I really want the exact area. If I want the total cost, I really want the exact area. I can live with some approximations, but I would like to determine the exact area. But the exact area requires a limit of the sum of the areas of each and every rectangle, of all rectangles, going to infinity. Okay, so now let's talk about this first. It's called summation notation, also called sigma notation. It really signifies sum, S, but we mathematicians, let me